Hello everyone, today we're going to be going over the June 2024 Physics Regents exam. In this video we're going to be focusing on part C, which is the final part of this exam and is fully made up of short response questions. A link to this test can be found in the description of this video alongside videos that go over part A, B1, and B2 of this exam. So if you want a full review, check out those videos in the description. That being said, we're going to go ahead and start off with number 66, which asks us to plot the data points for current versus potential difference. So here we have this whole blurb which is saying that students in the experiment measured the current and the voltage at different settings, and they recorded their data in this table below. What the Regents wants you to do is to go ahead and plot these data into a graph. And they'd be asking, well, where is your graph? Well, your graph is not going to be located in your test booklet, but rather in your answer booklet right here. So when you take the Regents, you're going to have a test booklet and an answer booklet. The test booklet is going to contain questions 1 through 85. Nothing in your test booklet is going to be graded. The only thing that's actually going to be graded is whatever's on your Scantron and whatever's on your answer booklet, which is right here. So on the Regents, you'll be given 3 booklets. The answer booklet, where you're going to write your answers and what's going to be graded. The test booklet, which is just going to be where all the questions are. And finally, the reference table, which is going to be as a booklet as well. Okay, so here's the graph. Here are my points. Let's go ahead and let's plot them. So the first point is 0, 0. The second point is 2, 0.26, which is somewhere up here. Or maybe a little bit lower. Remember that whenever you're graphing, you're given a margin of error of plus or minus 0.3 of where that point should be. So the Regents is pretty lenient with what they'll allow as what they'll consider a properly plotted point. All right. Finally, potential difference of 3. The current for that is 0.35, so we'll go ahead. 0.35 is somewhere around, or 0.35 would be below right here. Okay, 5 should be at 0.63, so 0.63 should be somewhere around here. And finally, at 8 volts, we're at 0.98, which should be all the way or almost up here. Okay, so that's all the points properly plotted. If you have trouble doing this, always make sure to figure out the scale. So in this case, you're going from 0 to 1 in 2 jumps, right? So just divide 1 by 2 and you get 0.5. So every single jump or every single tick is 0.5. And the same thing goes with the y-axis right here. So if we look at this, right, it takes us 2 jumps to go from 0 to 0.2. So 0.2 divided by 2 is 0.1. So every single tick box here is increasing by 0.1, right? So now that we have our points plotted, we get full credit for number 66, and then now it's asking us to draw the line of best fit. So in order to draw the line of best fit, I'm going to go ahead and I'm going to pull out my ruler. I'm going to place it onto my graph, okay? And the trick with drawing the line of best fit is you want to capture the most amount of points above the line as below the line. So you're going to go ahead and you're going to position a ruler, and you're going to start from the origin, okay? And from the origin, you're going to go ahead and you're going to try your best to draw a line that captures the same number of points above the line as below the line. So I think that I have my line of best fit set right here. If I just arrange it like this, I think this is good enough, right? Because I have 1 point on the line, 1 point below the line, 1 point below the line, and then 2 points above the line. So if your line goes through multiple points, that's even better. But you're really looking for the line to go through all of your points, or the line to have a similar amount of points above it as below it. So now that I have my line, I'm going to go ahead and I'm going to plot or draw my line of best fit. So like so, okay? Now remember, your line of best fit shouldn't really go off the page, of course, so I can go ahead and pretend like I didn't plot this point over here or this point over here. So maybe I can go ahead and redraw it actually, so that my line of best fit is actually on my paper. So let's do it like this, draw, make it in yellow so you guys can all see it pretty clearly. And like so, this is my line of best fit. So the next part of this question asks us to calculate the slope of the line that we just drew. So, and in this case, we need to show our all work, including the equation with substitution with units. So to show our work, we need to show them what the formula for the slope of a line is. And that's going to be y2 minus y1 over x2 minus x1, okay? So I'm going to have to choose points not from my table, but points that my line actually passes through. So in this case, I drew my line, and this is the reason why I drew my line, as passing through the point 0, 0. So that's a free point that we for sure know exists. So if our first point is 0, 0, that means that our x1 is 0 and our y1 is also 0, okay? Now let's choose another set of points that this line also passes through. And if we look at our line, we can see how it kind of passes through, or yeah, it does pass through the point 4, comma 0.5, or that it passes through the point 5.5, comma 0.7. Okay, so that's a very good point, right? It literally passes through that very nicely. So we can say that the second point that we're going to use is 5.5, comma 0.7. Okay, so if I want to calculate the slope, I can say that, not x1 minus x2 over x1 over y2 minus y1, but I can say that the slope is equal to, always say what it's equal to, that the slope is equal to x2 minus x1, sorry, y2 minus y1, remember y always goes on top, divided by x2 minus x1, x going bottom. So now the slope is equal to y2, which is 0.7 amps minus 0 amps, okay, divided by x2, which is 5.5 volts minus 0 volts. And finally, the slope, if you plug this into your calculator, is going to be 0.7 divided by 5.5, which is going to give you 0.12, or 0.13 if you round to the nearest hundredth, which is what I'm going to do, amps over volts. Always make sure to plug the units in and put the units in. Now, if you just box your answer, you'll get full credit for this section. For those of you that are using the actual answer key, you might find that the slope that you get is different from the slope that the answer key gets. The reason for that is because the answer key plotted their points differently from you, and they drew a different line of best fit. So as long as you're somewhere within an acceptable range, or you calculate your slope using points that your line goes through, you will not get points taken off for this, okay? So number 70 finally asks us to determine the resistance of the resistor. Now, if you want to find the resistance of a resistor, how do you find resistance? Well, if I look at my reference table and I scroll all the way down over here, I know that my resistance, where is it? My resistance is equal to voltage over current, or V over I. If I look at my slope, I have I over V. I have amps, which is my current, being divided by voltage. To find my resistance, I need my voltage divided by my amps. So what I can do here is I can just flip this. I can do 55 volts minus 0 volts divided by 0.7 amps minus 0 amps and get 55 volts over 0.7 amps. Guess what? Amps is current and volts is, well, voltage. So I can do 55 divided by 0.7 and I can get that my resistance is going to equal to 7.85 or 7.86 ohms. 7.86 ohms. That's what I am going to get as my answer here, okay? All you have to do is realize that your units here are in amps over volts. If you want to find the resistance, you do volts over amps. So number 71 says that an alpha particle with a charge of +2 elementary charges is moving towards two oppositely charged parallel plates, as shown in the diagram below. The magnitude of the electric field strength between the plates is 5.0 times 10 to the power 4 newtons per coulomb. Determine the magnitude of the charge of the alpha particle in coulombs. So I know that the alpha particle has a charge of +2 elementary charges, right? So I want to go from +2 elementary charges, which is E, all the way to coulombs, which is C. And just a quick note, whenever they say determine, and they don't put in brackets show work including substitution with units, you don't have to show your work, okay? So you can do this wherever you want. You don't have to show work up there. So if I have 2 elementary charges, how do I know how many coulombs that's equal to? Well, if I look at this first page right here, this is going to tell us pretty much a bunch of conversions. And here it says that 1 elementary charge is the symbol E, and that's equal to 1.6 times 10 to the power of negative 19 coulombs. So if that's 1 elementary charge, if I have 2 elementary charges, which is the actual charge, I can just do 1.6 times 10 to the power of 19, or negative 19, times 2, right? 2 times. I have 2 elementary charges, so I'm going to multiply this by 2. And as my answer, I'm going to get 3.2 times 10 to the power of negative 19 coulombs. Right? Number 92 says, on the diagram in your answer booklet, draw at least 3 field lines to show the direction of the electric field between the charged plates. Right? So field line is just the direction in which a field goes. And you know that in an electric field, it's going from positive to negative. So as long as you draw 3 lines between the positive and the negative plate, you'll get full credit for this, right? Because between the 2 plates, the field is just straight. It's a straight line from the plus end to the minus end, right? So here, here, I'm having a difficulty because I don't have a ruler right now. But let's say that that's a straight line. So from here to here to here. So this is a perfectly correct representation of the electric field. Just make sure to go ahead and draw your arrows, start at the plus, end at the minus. Now 73 is asking us what is the direction of the electrostatic force exerted on the alpha particle as it passes through the plates. So this alpha particle has a positive charge, right? It's plus 2 elementary charges. So yeah, if you have a positive charge and you know that the direction of the field is from positive to negative, is this plus going to be attracted to itself, or is it going to be attracted to the minus end? Well, if you know anything about electrostatics, you know that likes repel. So this positive charge wants to get away from this positively charged plate, and negatives or opposites attract. So it wants to, not negatives attract, opposites attract. So it wants to get closer to this negative plate. So it's going to be pulled towards and move towards the negative plate. So a correct answer for here could just be that the electrostatic force is towards the negative plate, or that the electrostatic force is to the left or away from the positive plate. I think the safest the safest option here is just to say that the electrostatic force is towards the negative plate. That's all we have to do, right? Just facing towards the negative plate because positive goes to negative, right? Now, number 74 to 75 asks us to calculate the magnitude of the electrostatic force exerted on the alpha particle by the electric field as the alpha particle passes through the electric field. So I want the electrostatic force, right? So keep that in mind. We're going to go ahead in our reference table, and we see here how electrostatic force is Fe, right? The electrostatic force. And we know that Fe is equal to kq1 over q2 over r squared. And you'd be saying, whoa. What's my distance? How am I going to use this? And you're right? We can't use this formula. Right, this formula is only when you have two charged particles. In this case, we don't know the charge of the plates, and we also don't know the distance between the two plates. So we can't use that. So that's a quick trap that the physics Regents set out for you guys, right? You wanted to solve for the electrostatic force. You saw, oh, this is in terms of Fe. I'm going to use this formula. That's false. You can't use this formula. You don't have enough information for that. Now, what other formula can you use? Well, you can use any other formula that has Fe inside of it, which is this one right here. You know that E, which is the electric field strength, is equal to Fe over Q. And guess what? The problem told you that the electric field strength was 5 times 10 to the power 14 newtons per coulomb. So if you go ahead and you say that E is equal to Fe over Q, you can go ahead and you can rewrite this in terms of Fe. If you multiply both sides by Q, you get that the electric field times Q is equal to the electric field strength, right? It's equal to the electrostatic force. So if you multiply the electric field strength by the charge, you'll get the electrostatic force, okay? So let's go ahead and let's write that down in our answer booklet. Remember that you need to write down the formula that you're going to be using, then you need to write down that formula solved for the thing that you're solving for, and then you need to plug in with units. So you're showing to the Regents graders that, hey, I know what formula to use. I'm going to use this formula. E is equal to Fe over Q. And then you need to show to the Regents grader that, hey, I'm solving for the right thing. In this case, I'm solving for Fe, which is the electrostatic force, and I'm saying that that's equal to E times Q. And finally, what you have to do here is you have to tell the Regents grader that, hey, not only do I know the right formula, but I also know the right values to plug in. So Fe is equal to 3.2 times 10 to the power of negative 19 coulombs. Always remember to put in your units. If you don't put in your units, you'll get it wrong. And that's times 5.0 times 10 to the power of 4 newtons per coulomb, right? Finally, if you plug it into your calculator, you know that you get a electrostatic force of 1.6 times 10 to the power of negative 14 newtons. Box that in and you get full points for this problem, right? So number 77 through 76 asks us to graph a wave produced in a spring, right? So let's read this problem. This problem says that two students investigate transverse waves using a long stretched spring. One student holds the end of a spring stationary while the other produces 12 waves every 4 seconds. The waves have a uniform amplitude of 0.2 meters, and the distance between the two adjacent crests is 0.4 meters. So they want us to go ahead and graph this or plot this out. Okay, and again, this plot is not going to be in our test booklet. It's going to be in our answer booklet, right? So here's what's important about this problem. We know that the distance between two adjacent crests is 0.4 meters. This is very important because this tells us our wavelength. Okay, the wavelength is a distance between two crests or two trows, or it's the distance that it takes the graph to go or to generate one crest and one trow. Okay, so when you graph this, you can graph this in many ways, right? Way number one, you can graph the distance between two trows. So you know that the amplitude is 0.2 meters, and you know that at a crest, that's going to be a positive displacement, right? That's going to be a positive amplitude. So your first point is at the first crest. And then you know that it takes the wave 0.4 meters to reach the next crest, right? Because that's the wavelength. So your second point should be here. And then finally, you just need to show one trow, and then you're going to be good. So every single section of this graph should be equal. So you should start here, then you should go to 0 here, then you should have your dip or your trow down here at negative 0.2 as your amplitude, and then you can go back up to 0 and then go back up to your crest. So this would be a complete and correctly graphed single cycle of this wave. Now, let's say you didn't like thinking about it that way. Let's say you want to graph it somewhere else. Remember that the wavelength is the time it takes for the graph to cycle through one peak and one trow, right? So let's say we start at 0. That means that in 0.4 meters, we will have cycled through one peak and one peak or one crest and one dip or one trow, right? So we know that if we start at 0, we're going to go up first, then we're going to go down, and then we're going to keep going down. So this is my peak, this is my trow. I'm going to connect it with this smooth and curved line. And again, this is another way of plotting out one cycle. So my point here is that there's many different ways to do this. What the Regents is looking for is for you to understand that the wavelength is 0.4 and that it'll take the wave 0.4 meters to complete one complete cycle, which is one peak, one trow, or two trows, or two crests, or two peaks. And that the amplitude is 0.2, so the height of this wave is only between 0.2 and negative 0.2, right? So now, number 78 is asking us to determine the frequency of the wave. And the frequency of the wave is just the number of cycles per 1 second, right? And that's frequency. Hertz is just per 1 second, okay? So if I know that I make 12 waves every 4 seconds, and I know that the frequency is the number of waves or the number of cycles per 1 second, well, I'll just divide the top and the bottom by 4, and I'll get that my frequency is 3 waves per 1 second. And that per 1 second, well, that unit is just hertz, right? So the frequency is 3 hertz. Remember that the difference between frequency and period is that period is the total amount of time it takes to complete one full cycle, whereas the frequency is, well, how frequently you complete one cycle, aka how many cycles do you complete in 1 second. Okay, so number 79 through 80 asks us to calculate the speed of the waves and to show all work, right? So if I'm calculating the speed of the wave, I'm going to go ahead and look at my reference table for the proper formula. I see that my speed of a wave is equal to the frequency times the wavelength. So I calculated the frequency to be 3 hertz, and I know my wavelength is 0.4 meters. So I can just write that my velocity, or my speed, is equal to the wavelength times the frequency. So my velocity is equal to a frequency, or let's do wavelength first, a wavelength of 0.4 meters times a frequency of 3 hertz. Okay, that means my velocity is going to be 1.2 meters per second. Right? So that's all we have to do to get full credit for this problem, right? So moving on to number 81, it says that an alpha particle, or that alpha particles are stable decay products of many nuclear disintegrations. An alpha particle consists of 2 protons and 2 neutrons and has a mass of 6.644 times 10 to the power of negative 27 kilogram. When the individual masses of 2 protons and 2 neutrons are added, the sum is 6.695 times 10 to the power of negative 27 kilogram. The difference between the mass of an alpha particle and the total mass of its 4 individual components particle is called the mass defect. So what this problem is saying is that an alpha particle, let's just say that's a big A right here, normally has this mass right here, right? Or rather, let's think about it this way, guys. The alpha particle is made of 2 protons and 2 neutrons, meaning that if you add up the weight of those 2 protons and 2 neutrons, an alpha particle should weigh 6.695 times 10 to the power of negative 27 kilograms. In reality, right, as this alpha particle is released, it has an actual weight of 6.644 times 10 to the power of negative 27 kilograms. So what happens is, as this particle is released, it loses mass, right? And it just said that the difference between the mass of the alpha particle, which is in green, and the total mass of its 4 individual components, which is the 2 neutrons plus the 2 protons in blue, is called the mass defect. So if they want us to find the mass defect in kilograms, guess what? all we have to do here is just figure out, well, how much mass is lost when this alpha particle is emitted or when this alpha particle is formed, right? So technically, when an alpha particle is formed, those two neutrons and those two protons should come together to have a mass of 6.695. In reality, they have a mass lower because some of that mass is converted into energy. So to find the difference between that, we'll just do 6 in our calculator, 6.695 times 10 to the power of negative 27 minus 6.44 times 10 to the power of negative 27 kilograms for both of these, right? Again, they're not asking us to show us work, so we don't really need to plug in units. And what you'll get here, when you plug this very, very long formula into your calculator, is that the mass defect is 5.1 times 10 to the power of negative 29 kilograms. If you are confused as to which value to subtract first, think about it this way. Can mass be a negative number? No, mass is not a negative number. Even though you're losing mass here, technically, you already know you're losing mass, so you don't need that negative to symbolize that, right? The defect already shows that you're defective on your mass, right? You're decreasing your mass, right? Number 82 through 83 asks us to calculate the total energy in joules that would result from the complete conversion of this mass into energy. So if I'm going into mass, and I'm going from mass to energy, what's one formula on my physics reference table that combines mass and energy? Oh, look at this, modern physics, E equals mc squared. That's the formula I'm going to use here. So on my answer booklet, I'm going to go ahead and I'm going to write that E is equal to mc squared. What's c again? Well, c is my speed of light in a vacuum. And if you don't know the value for that, you can go ahead and scroll up here to these constants, and it'll tell you that c is 3 times 10 to the power of 8 meters per second. So you know that the energy released is equal to the mass that was lost, which is 5.1 times 10 to the power of negative 29 kilograms, times c, which is 3.00 times 10 to the power of 8 squared. Okay, so now that if you plug this into your calculator, you'll get that the energy released is equal to 4.6 times 10 to the power of negative 12 joules. Okay, so if you go ahead and box that in, and we can go ahead and we're going to move on to number 84. Now, 84 asks us to determine the total amount of energy that would result from the complete conversion of this mass defect into energy in mega electron volts. So right now we have energy in joules, but I want to convert joules into mega electron volts. So let's see what we can do. Whenever you're converting units, that's probably going to be found in the list of physical contacts or physical constants. So if we look here, we know that 1 electron volt is equal to 1.6 times 10 to the power of negative 19 joules. So to solve this problem, we just need to pay close attention to the units, okay? So right now, what I have is I have 4.6 times 10 to the power of negative 12 joules, okay? Now, I can do two things. I can either divide by the conversion factor. I know that 1 electron volt, not mega electron volt, but electron volt, is equal to 1.6 times 10 to the power of 19 joules, or 10 to the power of negative 19 joules. So I can either multiply 4.6 times 10 to the power of negative 12 by 1.6 times 10 to the power of negative 12, or I can divide it. In this case, I'm going to divide it because guess what? Those units are going to cancel out. If I divide this by 1.6 times 10 to the power of negative 19 joules, these two joules are going to cancel out, and I'm going to be left with electron volts. Another way to look at it was through dimensional analysis. So this is 4.6 times 10 to the power of negative 12 over 1 times 1 electron volt, which is equal to 1.6 times 10 to the power of negative 19 joules. Either way, you're dividing by 1.6 times 10 to the power of negative 19, but if you set up the dimensional analysis, it becomes a lot clearer as to why you're dividing, because you're trying to get rid of these joules so that your final units are in electron volts, okay? So if you go ahead and plug into your calculator 4.6 times 10 to the power of negative 12, and you divide that value by 1.6 times 10 to the power of negative 19, you get that this is equal to, I'm plugging into my calculator as we speak right now. You get that this is equal to 2875000, right? So this many electron volts. Now remember, we're looking for it in mega electron volts. And if we look at our reference table here, we see here how mega is the prefix for 10 to the power of 6. So if this is in electron volts, 1 mega electron volt is equal to 10 to the power of 6 regular electron volts. So if I divide this by 10 to the power of 6, I can convert this electron volt into a mega electron volt. Okay, so if I divide this by 10 to the power of 6, I get an answer of 28.75. Okay? So 28.75. I can either leave that as 28.75, or I can go ahead and I can round that up or round that down. I'm going to go ahead and round it up to 29 mega electron volts, right? Just to keep it a nice even number. So, well, not even, but because 29 is odd, but just a nice whole number rather. Okay, so I hope that made sense for you guys. Remember, just use the dimensional analysis, right? I know I didn't use dimensional analysis for this part, but if you just think about it, I could still use it here. I know that there are 10 to the power of 6 electron volts in 1 mega electron volt. So I'm actually dividing by 10 to the power of 6 to cancel out that electron volt. And then finally, number 58 asks, what fundamental interaction is primarily responsible for holding protons and neutrons together in an alpha particle? So proton and neutrons are located where? They're located in the nucleus. Okay, and the force inside of the nucleus that holds it together is called the strong force. Okay, so that's all you have to write here. Strong force. That's the force that's holding the nucleus together. Okay, the force that's kind of pulling the nucleus apart is like an electrostatic force. But again, the strong force is the strongest force in the nucleus, and that's what helps keep that nucleus stable and together. So that's the end of this section. That's actually the end of this exam. So that's essentially, I've completed numbers 1 through 85 and uploaded my explanations through part A, B1, B2, and C. You can watch all those videos. I've linked them all in the description of this video. If you have any questions on what I did today, please let me know in the comments down below. I'll try and get to your questions as quickly as possible. That being said, if you have any other Regents subjects that you're trying to study for, I offer Regents review in many different subjects, so not just physics. Make sure to check those playlists out in the description if you want more Regents help. I hope you guys like this video, and I hope you guys learned something, and that you guys have a nice night.